and today I'm going to talk about some optimizations. Just a minute. Okay, and I work at Ambiata, and at Ambiata we use simple models to predict the future. And this is my boss with his eyes closed. And when he opens his eyes, he tells me that we need an enormous amount of input data in order for these models to be predictive. And processing all of this data is expensive. In fact, we're in an interesting situation where it costs us more to run our code than it does to develop it. So where does this leave us? I mean, are we back to C++, the so-called king of performance per dollar? Well, unfortunately for us, or perhaps fortunately, correctness is our #1 priority. Our customers pay us for accurate predictions, and if we make mistakes, our reputation or perhaps our business or the contract is at risk. So what's a developer to do? Well, we do what Haskell does best. We build a domain-specific language. We need a language that hits the sweet spot for expressiveness, but one that is restrictive enough for us to efficiently execute. And this is all well and good, but the key to delivering on this promise is that we build an optimizing compiler. A compiler that produces the kind of C that you would never want to write by hand, but that runs crazy fast. And for Ambiata, this means Icicle. Icicle is a query language for time series data, and it guarantees with its modal type system that queries are restricted to a single pass over the data. In case you missed Amos's FHPC talk, this is what an Icicle query looks like. Here we're taking the latest 5 values from some time series, and then we're going to compute the min of some of those 5 values. The Icicle compiler takes this source language through a number of different intermediate representations on its way to efficient C code. So how do we get from the icy mountaintops to the depths of the sea? There's a lot more than I can cover in 20 minutes, so I'm just going to tell you about 3 optimizations which we found particularly useful in our compiler. Schema specialization, partial evaluation, and data flattening. So let's start with schema specialization. I often hear developers say that their code is I/O bound, and I find that very hard to believe. When you say that your code's I/O bound, I just think you're saying it's 1996. That was the year the quantum fireball was released. It was 7.6 megabytes a second of glorious spinning Rust. And I want to share with you the reality of today. I benchmarked this laptop before I left the hotel this morning, and it managed to achieve 1,800 megabytes per second sequential reads. And if you think about that on a 2.5 gig processor, that gives you about 1.3 cycles per byte. And you can't do much with that, maybe add an integer. I also had a look on the internet and found that the fastest SSD that you can get these days is 3,300 megabytes a second, so things are not going to get any better. So let me tell you, you're going to have to work awfully hard to saturate a hard drive today, and so there's no way that you're I/O bound. Your code is just slow. So where do we start? Well, if you want highly performant code, then getting data into the system efficiently is the first step. Otherwise, the rest of the code's not going to matter. Most recently, I needed to pass this format. It's the one true enterprise format with the twist of Web 2.0. And the main point that I want to focus on here is that to achieve good parsing performance, you need to avoid reading 1 byte at a time. You need to read multiple bytes at a time. So how are we going to do this? Well, because Icicle programs are compiled at runtime, it means that the parsing code can be made to work exactly for the expected input. And we're going to exploit what we know about this schema. So what do we know about this schema? Well, we know that the row can't contain a line feed, and that's always the termination for the row. We know that these first 2 fields can't contain a pipe. That's part of the schema. And so what we could do is use a C function called memchar to process multiple bytes at a time and locate these tokens. Efficient implementations of memchar are implemented using SIMD, so they can scan multiple bytes at a time. And in Haskell, you can get access to this with the data byte string lmindex, which uses memchar under the hood. So what about this pipe? You might have noticed we missed one, so how are we going to get that? Well, we know that the date is always exactly 10 bytes, so we can scan backwards 10 bytes and locate the token. And so we're good. We've located all of our separators without kind of breaking the bank. What about the contents of the columns? Well, we know this is a well-known schema. We know it's either going to be lang or data in a valid column. And we also know the schema of the JSON, so the SH and whether this is a Boolean is well known. So you might think maybe these look like strings to our parser. But I don't know, if you look a bit closer, maybe they're 32-bit integers. And in Icicle, that's sort of exactly the way that we treat strings. They're lists of 64-bit integers, and we process them as such. So if we take a look at some generated code that the Icicle compiler will produce, we can see that here we're looking at the first character, which is the word adjusted, and we're processing that 8 bytes at a time. And then here we look at the second part, which is underscore close. And you'll notice that we need to kind of mask out the last 2 characters because we're not interested in those. You might think this is unsafe, but we always make sure we pad our buffers with an extra 8 bytes so that this is always safe to do. So the key point here is read multiple bytes at a time where possible. This is going to be our best weapon for getting good parsing performance. Okay, so we have our data loaded. What's next? One avenue for optimizing programs is a technique that we like to call partial evaluation. Now, our compiler uses a very simple partial evaluator, and we'll see how that works a bit later. One of the reasons we want to do this is because we need to get rid of any lambdas that are in our source language so that we don't need to compile them to C. Now, you might be thinking, given we compile to C, don't GCC and Clang already do some of this kind of thing already? And they really, they do attempt to. And given all of the hazards they have to worry about, like pointer aliasing and phi nodes, and the fact that jump labels are different from functions, even though that's the same thing, they do a pretty amazing job. But they just don't have as much information as we have at our high level of abstraction. So one thing that's interesting to note is that Icicle is a pure and total language, and so we don't need to worry about evaluation diverging. We can just keep evaluating everything until we run out of things to do. So our partial evaluator is a mix of 2 transformations, just beta reduction and constant folding, and I'm going to give you a quick tutorial on what those 2 things are. So beta reduction is the process of applying a lambda to a constant, applying a lambda to an expression. So first we're going to look at the binding for the lambda x, and we'll see that we use x just once. So we're going to replace it with the target of the application, like so, and then we replace the entire expression with the body of the lambda. So that's beta reduction. Constant folding is the evaluation of primitives applied to constant arguments at compile time rather than runtime. So if we go back to our example, here we have 9 plus 1. We see that this is a primitive application, and these 2 are constants, and so we can evaluate it at compile time, and we get 10. Let's look at a real example. You might imagine that you have some Icicle source code that looks like this. We just have 2 case expressions, and then they're used down here at the bottom. Now, the first thing that, one of the things that happens to Icicle source before we compile it to our intermediate language is that we just inline everything. So I'm going to inline bar, and now I'm going to inline foo. And so you can imagine that we have something like this. And you probably wouldn't write this by hand, but we have something like this. So now we translate that into our core language. And our core language doesn't have case expressions. We just have lambdas and application and a few other things. So the case analyses get turned into folds over the data type. And this is where we're going to begin our partial evaluation. So one thing that's interesting to note is that fold either and fold maybe are primitives of the primitives in the core language, so they can't be beta reduced. So we try and do constant folding now. Now the partial evaluator proceeds bottom up, so we look at the leaves first, and that means that we find this expression here. We'll see it's a constant used with a primitive operation and another constant, so we can constant fold that to 65536. Nothing left to constant fold, so now we go back to beta reduction. We come and have a look at this fold maybe sub-expression. We can see that these two guys are constant, and this isn't constant, but actually we know just enough information that we will still be able to evaluate this at compile time. So we see that we'll take these two guys and pull them out there. So the sum, or like the just case, now gets the x, and we can peel off the just and throw it away. So that's reduced nicely. Now we can go back to beta reduction, and we'll notice we've got a lambda applied to an expression, so we can reduce. And now back to constant folding. We can see we have just the right information that we can constant fold this. Back to beta reduction, we apply, and we're done. So you can see we've applied beta reduction and constant folding in tandem, and we've managed to evaluate a bunch of our program, and the key thing for us is that we've got rid of all the lambdas, so it's easy to compile to see. Because we're working at a higher level, we can evaluate things that are kind of out of reach for Clang and LLVM. Okay, so removing lambdas made it easier to compile to see. Is there anything else that needs taken care of here? So we're onto our final transformation, and the general idea here is that we want to take our complex data types and melt them down into primitives like bools, ints, and doubles, so that so they're easy to compile to see. And yeah, that's the initial reason why we did this, but there was a bit of a surprise along the way. Now this is one possible solution. We might take a record type like price here and just convert that to a C structure. And then maybe maybe we can represent that with some kind of tag and then the payload. But we kind of didn't want to do this because all of the polymorphic types like either and maybe an array would generate this sort of explosion of data types. So we decided that was out. Another possible solution might have been to use C++ templates, and this would have alleviated the problem with polymorphic types. But we really didn't want to use C++ as an intermediate language. The advantage, I feel, at least with something like C or LLVM as a compiler target, is that you can fairly easily predict the assembly or the performance that you're going to get when you're looking at it. And I sort of thought if we use C++, then we might have been tempted to push more things down into the higher level abstractions that it offers. So we didn't want to do that. It was no good either. Now, I wasn't... some people didn't agree with this decision, but and one day I came back into work and the backend had been converted to C++, and so that kind of motivated me to finish this flattening transform. And let me tell you, there is not a single thing on this planet that will motivate you to write code more than the threat of C++. Something that we were surprised to find along the way is that doing this transformation sort of exposed some additional optimization opportunities, and we'll see that at the end. So how are we going to melt down our data? Well, there's going to be two premops that we're going to use to do that. But first I'll sort of show you what the melted data looks like. So now we go back to our price, and we see that simply gets melted into 3 integer variables. Maybe price gets melted down into 4 variables with a tag to say whether it's just or nothing. And then this is sort of where it gets a bit more interesting. If you have an array of maybe price, that gets melted down into 4 arrays. So now all of the data is kind of packed nicely in memory, and you get good memory locality, which was perhaps unexpected. Let's take a look at unpack, which is the first of these transitional primitives which are going to help us. The type of unpack looks a bit scary. So the general idea is you are going to take the index of You're going to give it the index of the field that you would like to pull out of the compound type. You're going to give it the compound type, and then a value of the compound type, and then this thing at the end is just to sort of compute what is the type of the value that you're extracting, and this will make more sense with an example. So here we see in the maybe example, the first one, if we want to take the 0th field out, we pass it 0, we pass it the type, maybe price, and it gives us back a function, maybe price to bool, which lets us extract the melted down value out of it. So the opposite of that is going to be pack, which is going to allow us to take a bunch of our melted down values and smash them together into a compound value again. So you see it takes a type and then all of the components, and then it will give us back our composite, our compound type. And this is what it looks like for maybe. So we give pack the type maybe, and then it gives us back the function that will smash everything together again. So if we look at a real example, here we've got an icicle query that's taking the latest 5 of some time series and then summing up the high value. Maybe this query is not that useful by itself, but you might do it on the way to computing something else. So this source goes through a number of representations until we get to avalanche, which is our imperative representation that we convert to right before emitting C. And I'm just going to quickly walk you through this so that you know what's going on. We've got this buff 5, and that is a circular buffer which can contain 5 elements, and that corresponds to the latest 5 in the original query. So we initialize some accumulator, we walk over everything in the input set, pushing each one onto the circular buffer, and then the old ones kind of fall off the back. Then we initialize another accumulator, which is going to be for the sum, and then we loop over the 5 values in the circular buffer, and we sum them up in the accumulator. Okay, so now we know what this does. Let's perform some data flattening. So I'm just going to move this over here so we've got a bit more space. So the first thing we want to do is insert all of these pack and unpack primitives, and that's going to allow us to melt the instructions into primitive ones rather than compound ones. So we're going to start at the top and work our way down. We start with this initialization, and we see that we have a compound buffer, so we need to melt that by inserting unpacks. So we've applied unpack here. Now we're going to, we come over this loop over prices, so we're looping over compound types. We need to melt that into primitive types. We do that. That means we need to sort of substitute in the rest of the program and insert a pack so that it still is type preserving. We come to this buffer, which we melted earlier, so we need to melt that. And that's where these names come from. We have some sort of convention so that as we work top to bottom, we know what the melted buffers should be. All right, now we need to substitute for x's to account for the fact that we melted those buffers, so we insert a pack. I'm just going to move these guys over here. And then we need to melt the right to the buffer. So we melt that into 3 as before. And you can kind of see a pattern here. So we find a read, we melt that, and we go and fix up the stuff later in the program and insert a pack, and we're done. So what was the point of all that? We just kind of like blew up the program and inserted all of these pack and unpack things. So now we need to kind of eliminate them so that we have something a bit simpler. So we go back to our program. We find these unpacks. We're just unpacking something that was constructed with an empty compound type, so we can just replace that with the empty primitive type. We have this dance of packing and unpacking, so we can just go straight to the original buffers that we had, and then back down here we pack up a buffer only so that we can index into it and pull out the high value. So we could just index into the high value instead. And now we're left with our final program. And it's sort of interesting, but we notice that after doing this, we have some optimization opportunities. If we come and look at our program again, we'll see that all of this grayed out stuff is now dead code because we were only using the high value. And so now, if we eliminate that, we don't need to cart around all of these extra fields that we weren't using. And now we're left with something that is pretty much like what we started with, except that we've eliminated all of the compound types, so it's easy to compile to C. And we have also done some dead code elimination, so there's some extra computation which we're avoiding. So someone once compared C++ to building an octopus by nailing legs to a dog. So if you're not into veterinary surgery, and if performance matters, you can afford to write a compiler for a domain-specific language that hits the sweet spot for expressing your problem, but is restricted enough to allow for efficient execution. You can process multiple bytes at a time and push the limits of I/O. You can work at a high level and do the kinds of optimizations that LLVM can only dream of. And you can melt down your data and expose great memory locality and additional optimization opportunities. So when performance matters, you don't need C++. You can do it all in Haskell today. Thank you.
And Klepper, Google. I have a question. So if you work over time series, the time series has a tendency to, the schema of the time series has a tendency to change over time, right? Because that would usually, so how does the system would deal with that on the boundaries?
We don't deal with that. So our system's just limited to sort of fixed schemas. I suppose our schema could evolve at a later date, sort of day to day, but then you would need to go back and run your query from the start again.
Okay.
Hi, Gergordy. Can you go into some detail of the definition language for the data schema thing? Is that just a fully static declarative description, or is that like extracted from program which you write in the naive way, which parses it? Or so where exactly is the format spec originating from?
Yeah, so the schema is, so the question was, can you describe, yeah, you've got the, sorry, I didn't, yeah, anyway. The schema is described separately in a dictionary, and it's not inferred from the program. So we don't support too much at the moment. That's sort of a legacy constraint that we just have like records and lists and these kind of things, but where the language itself supports some types and all kinds of algebraic data types. So we would like to add that to the schema description language as well.
Chaz Leichner, X. So the statement that we basically got 1.5 operations per read strongly assumes a CPU. Have you considered other ways of processing your data that might give you a lot more throughput?
So we haven't really considered GPUs or anything like that. I suspect for our case that putting it onto the GPU or transmitting the data to the GPU would be perhaps yet another bottleneck. So our data set sizes are in the realm of sort of 10 to 100 terabytes. And I don't know, perhaps it would be a good solution if we had a really compute-heavy query that we wanted to run, but we're just fine on CPUs at the moment.
So your system does apply a lot of amazing transformation, like transforming the data structure, introducing the loop buffer, memory optimization, and dead code elimination. So how do you make all these operations composable and compose correctly? What is the key?
Nothing too fancy. We just run them one after another, I suppose. It's kind of the. I'm not sure of a good way to do that.
How you are doing this?
How we're doing it, we sort of, we have some passes which sort of run, so if you think about the beta reduction and constant folding, those two run in tandem until we reach a fixed point. So we actually have a fixed point monad transformer which Avos has written that allows you to denote whether you've made progress or not. So instead of saying return, you can kind of say, I made progress, like return and I made progress, and that means that when you come back around, you know that you should run again. So that's perhaps a nice way to have a couple of transformations which depend on each other and just run them over and over again.
Let me have a look at. Thank you.
Okay. Thank you, Jacob. We're going to have a break and reconvene at 3:20.